Neurons can be thought to physically realize informational criteria placed on characteristics of their input, which, if met, trigger neuronal firing. But how do they do this? To answer this, we should first consider a fundamental puzzle in neuroscience. Why do neural networks bother with relatively slow chemical transmission between neurons at the synapse when electrical communication between neurons would be much faster? Put another way, why is there a synaptic cleft at all? One answer could be that evolution cannot easily come up with an unbroken reticulum because such a reticulum would have to be constructed of cells, and cells are by their very nature discrete entities. However, there are instances of networks of discrete neurons that communicate using so-called gap junctions, which are essentially little pores that link abutting neurons. Gap junctions allow direct transfer of charge and therefore depolarization and hyperpolarization from neuron to neuron extremely quickly. Networks of neurons linked by gap junctions are tantamount to a continuous reticulum since gap junctions allow potential to flow directly from cell to cell. So cellularity alone cannot explain why the nervous system relies on chemical transmission at most synapses. There has to be some advantage to slow chemical diffusion of neurotransmitter across the synapse, or there might be some disadvantage to the fast transfer of charge afforded by gap junctions. An alternative answer to the puzzle of why there's a synaptic cleft arises from an understanding of neurons as criterial informational decoders of their inputs. Neurons keep their intracellular potential discrete because they each impose their own discrete set of criteria for firing on their inputs. This guarantees that neurons respond only to their own inputs and not to the inputs of other neurons. If neurons were linked by gap junctions, they could not realize discrete criteria for firing based upon summation of intracellular potential, since depolarization of one cell would automatically lead to depolarization of abutting neurons. To enact discrete criteria for firing, it's necessary to keep the summation of potential in one cell entirely separate from that in another cell. In fact, discrete criterial assessments require discrete compartmentalizations of the summation of potential, not only at the level of neurons, but also within neurons. This may account for the compartmentalization of potential within dendritic arms and spines as well, because neural computations can happen in the dendrites as well. Criteria are physically realized, in part, at the level of receptors in the postsynaptic cell, and receptors are by their very nature chemical in the criteria that they set, owing to the binding of the neurotransmitter molecule with the receptor. Thus, all complex nervous systems that we know about have evolved an alternation between electrical communication, which is not criterial once a ballistic action potential has been set in motion, and chemical communication allowing discrete summation of potential within each neuron. Physical compartmentalization of potential summation, when combined with a physical assessment of potential level relative to a threshold for the release of some subsequent physical process, such as the firing of an action potential, realizes the specification of discrete informational criteria placed on informational inputs, which, if met, change the physical state of the brain by triggering neural firing. In other words, the meeting of informational criteria changes the physical brain and thereby the physical universe. Criterial satisfaction and flexible changing of neuronally realized criteria is how information becomes causal and how top-down mental causation also becomes possible. Independent informational criterial assessments require compartmentalization of potential. This necessitates a means of communication between neurons that is not reliant on gap junctions, because gap junctions would decompartmentalize physical potential and therefore make informational criterial assessments non-independent. Given that having a synaptic cleft is necessary if informational criteria are to be evaluated independently of the decisions made by other neurons, evolution might have harnessed the existence of the synapse for other purposes. In other words, chemical transmission between neurons, although slow, might introduce additional advantages. A central reason why chemical transmission at the synapse may be beneficial is that neurotransmitter diffusion across the synapse introduces a source of variability in the timing of postsynaptic neuronal responses. Variability, or noise, in neural activity can be harnessed by a neuronal system that realizes discrete criterial detectors to generate novel solutions that meet any given set of neuronally realized criteria. How is this variability realized within a single postsynaptic neuron? Well, variability exists in the arrival time and magnitude of single postsynaptic potentials or currents because of neurotransmitter binding to postsynaptic receptors and their consequent reconfirmation. This translates ultimately into variability in the timing and rate of firing of postsynaptic neurons. This variability has multiple potential independent sources. First, there's variability in the amount of neurotransmitter in the synaptic cleft due to variability in the amount contained in vesicles, and therefore in the amount released presynaptically. Second, there's variability in how receptors themselves respond to neurotransmitter binding. And third, there's variability in the size of the synaptic cleft, which is the distance between the neurotransmitter release site on the presynaptic neuron to the site of receptors on the postsynaptic neuron. Scientists who have modeled the synapse using a three-dimensional random walk, meaning a Monte Carlo algorithm mimicking Brownian motion, have found that distances greater than 300 nanometers lead to essentially no postsynaptic response. It is therefore most likely not a coincidence that the synaptic cleft is typically on the order of 20 to 40 nanometers. There would be little variability in arrival times of neurotransmitter as it diffuses across the synaptic cleft if the synaptic cleft were just 1 nanometer wide, because the random walk of diffusion would not have much distance over which to introduce variability in arrival times of neurotransmitter. Conversely, if the cleft were too big, say 300 nanometers wide, the neurotransmitter would hardly even arrive, and even if it did arrive, it would take too long to get there. A reasonable hypothesis, then, is that the cleft has evolved to be the size that it is because this permits the introduction of an optimal level of variability in postsynaptic potential onset time, given neurotransmitter diffusion rates in brains that have our temperature and physical makeup, and given the need to arrive quickly. In effect, diffusion across the synapse is one of several physical mechanisms that permit the amplification of microscopic fluctuations into macroscopic variability in spike timing. In a coming section, we'll consider other such processes of amplification that bring indeterminism from the quantum domain up to indeterminism at the level of spike timing among criterially responsive neural circuits.